Hello and welcome to today's lecture on propositional logic. There are many ideas in mathematics and in computer science that I'm hopefully going to present by the end of this course, but I guess the fundamental building blocks for any mathematical theorem or a collection of mathematical theorems, as well as any theorems in computer science or in many other areas, they all have one fundamental building block, and that's the idea of logic. Specifically, we have a system of what's called propositional logic. And this is the first system of logic that anyone should be familiar with when they're going to try and construct a mathematical proof. This is really the basic building blocks of any mathematical statement. The next set of, I guess what we'll be doing is we'll be starting with propositional logic, and then we'll move on to what's called predicate logic. Most mathematical statements can actually be written very, very nicely using this formal language of predicate logic. It's kind of based on propositional logic. So today we're going to start with just going over propositional logic and defining what I mean by propositional logic. So propositional logic is a language, essentially. You can think of it as a new language that's based on what are called propositions. So let me define for you right now what a proposition is. Our first definition is going to be the following. We say that a proposition in propositional logic, we normally will use letters. Typically for one proposition we use the letter P. A proposition P is a variable that takes one of two possible values. So we say either the value true, which we typically will denote with a T, or the value false, which we denote with the value F. So a proposition P is a variable that takes either true or false, and all of propositional logic is built up on this assumption. So we assume that a proposition is in some sense, it's a statement that's either true or false. And I guess from the beginning, we need to understand that this is exactly how a proposition is defined from the viewpoint of propositional logic. In particular, it's not the task of propositional logic to decide whether certain complex statements are true or false. So for instance, an example of a proposition could be there is extraterrestrial life. But the idea is that this is a statement that is either true or false. But the idea is that we don't necessarily know whether it's true or not, and it's not the goal of propositional logic to tell you whether or not a statement is true. It simply deals with the relationship between statements that are either true or false. So any statement that you make in propositional logic has to be either true or false. And it just deals with the complete proposition as a whole, assuming that it's either true or false. There's no deeper meaning to it than that. And it's really not the task of propositional logic to decide whether a certain statement is a proposition or not. It's important that you understand this, because a lot of students will sometimes see the definitions for propositional logic and think that you can make a proposition to try to determine whether or not a certain statement is a proposition or not. But this is not the goal of propositional logic, and in some sense this will lead you to what's called a contradiction. So we'll go into that a little bit later. But so for instance, if I write down the statement, in winter is colder than outside, that statement has no real meaning to us in English language, but it's not the idea of propositional logic to determine whether or not that's a proposition. In this particular case, that statement seems kind of meaningless, actually. But the main idea here is that it's our job as smart mathematicians or computer scientists to provide meaningful propositions when we go to set up a theorem and write down a certain mathematical theorem. So the next definition that we have to make is that of a tautology versus a contradiction. And this in some sense is to define the two very, very special forms of propositions, so or very special types of proposition. We say the following: that a proposition which is always true is called a tautology, and likewise we have that a proposition which is always false is called a contradiction. So I'm going to underline the definitions here. There are two very, very big definitions and very, very different but very, very special types of propositions that we can have. The reason that these are special is because there's a number of different reasons, but one of the main reasons is that if I can show a certain combination of logical operators on propositions are a tautology, then I've effectively shown that it's a true mathematical statement. It's always true no matter what. And likewise for a contradiction. If I can show that a certain statement is a contradiction, I can show that this is a false statement. If something leads to a contradiction, it's a false statement. So this is actually a method called proof by contradiction. We use this idea to prove stuff, but in order to really kind of understand that, we need to get a little bit more deep into this propositional logic. So in a few lectures or so, we'll start talking about what it means to prove a statement mathematically. But for now, we're just going to kind of focus on getting some of the basic terminology down, and specifically some of the basic operations that we can do between propositions. This is the first thing that we'll talk about, which is the idea of a logical operation or a logical operator. So I'll use those two terms interchangeably. I'll talk about logical operator and or operation. But the main idea here is that for a given proposition, so we'll put here for one or many. The many case we'll start with one and then move on to many. For one or many given propositions, a logical operator is a new proposition whose truth value depends on input propositions. And makes sense that we need to start with the logical operators that have one input proposition, and then move on to higher and higher and higher, more and more complicated mathematical statements, because this is the underlying language that we'll be using to phrase mathematical statements. The most logical place to start with is a logical operator that has one input proposition. This is what's called a unary operator. This is a unary operator is a logical operator with one input proposition. And the nicest way of writing down what, like, the total number or the total amount of unary operators that we can have on one single input proposition is the following. We can have so let's say we just kind of draw this right here. I'll draw our P for our proposition, and we think about what's called the total number of possible truth values that P can take on. We know that because P is one proposition, we need to say write the possibility that P is true and the possibility that P is false. So what I'm doing right here is actually what's going to be a very, very important idea. It's what's called building a truth table for P. And already I'm hope that you can see that this idea is going to be able to extend very nicely to what are called binary operators, or two operators that depend on two input propositions. It can also be used for ternary operators and so on and so forth. This is going to be a big tool in our toolbox for discrete mathematics. But I guess the first big tool is this truth table that we're going to be using. So let's see how to kind of construct this. We'll see. Well, without any formal notion of what it means to count a set, we can't formally count anything really yet. But we can kind of do some basic counting, which will be justified a little bit later on in the course when we get into what's called cardinality of sets in set theory, and when we really start talking about what it means to do counting in mathematics, called combinatorics. So without any of that, we can only kind of rely on basic ideas of counting, basic methods for counting. But this is going to be fine for us right here. And specifically, you can ask yourself the question, how many unary operators should there be? Is there a finite number of unary operators? And the answer is yes, because we have a finite number of inputs to our proposition. Really, we have two possible inputs to our proposition, true or false. And what that means then as well is that because we have two inputs to a proposition, that any operator, and I'm just going to I'll draw a line right here and draw some general, let's say we define some general operator star that acts on P. For example, let's say star is some given unary operator that acts on P. Well, we have a total of two possible choices here for the first component, or the truth value here, star of P when P is true, can be either true or false. And likewise, star of P when P is false can be two possible values. So because of this relationship, then we say that any, or it could be some arbitrary operator star, any unary operator has a total of 2 times 2 possible outputs, which means that we have a total of 4 unary operators. And this is a nice method to learn, to know, because this idea is exactly how we're going to do this for binary operators and then beyond, ternary operators as well. So let's look at what these are. Well, the most fundamental operator, I'll say, is probably the identity operator. So you can do ID of P. And what the identity operator does is it takes in the truth value of whatever P's truth value is, and it gives back the whatever the matching truth value is of P. So, for instance, the identity operator of P when P is true. The identity operator of P when P is false is false. You can very clearly see that this is the most basic possible operator that we can have. The next the next operator is a very, very important operator, and its symbol goes like this. You put this sign right here, and then P. There are a number of different competing symbols that are used. The book that we're going to be using uses one notation. I will try to stick to the book's notation as close as possible, but be aware that the book sometimes uses different notation than I do. So if you ever have a question, please ask me as soon as possible so that I can clarify what notation I'm using and whatnot. But what this stands for right here, if this right here is the identity operator, this operator is what's called the negation operator, or the negation of P. And in the truth table, the negation of P should stand for the opposite of P. So we have that here, that if P is true, then the negation operator of P has to be false, or the opposite of whatever P is. And likewise, if P is false, then negation of P should be true. We're going to see that this negation operation is extremely, extremely important in mathematics. Certain statements can be made, and certain proofs rely very, very heavily on this idea of negation. And sometimes it's easier to prove the negation of a certain statement than it is to prove the statement itself. But the idea here is that if you can prove that the negation of a statement is true, then the statement itself has to be false, because every statement in propositional logic has to be either true or false. This is a very, very important idea. I guess these are the first two operators. We're supposed to have four here, and I'll quickly go through what the next two operators are. We have the tautology operator of P, and this is where the book uses a little bit of different notation, but I like this capital T of P. What this says is it's the tautology operation is exactly what we talked about before with tautology. It's no matter what the input value of P is, the tautology operator will always evaluate to true. So this is exactly how we define the tautology operator. And lastly, that we have what's called the contradiction operator, and no surprises here. The contradiction operator, acting on a proposition P, gives us that no matter what the input of P is, we have a false value for the value of the contradiction operator. So this is nice. This is a very, very nice expression of all of the logical operators that can take in a single proposition. Right? These are all the possibilities. There's no other possibilities here, because this table right here, clearly the truth table, clearly shows us any and all possibilities that we can have. If I have an input proposition that has to be true or false, the only propositions that I can have that are a function in some sense, we haven't defined that yet, but a function of true, the P, all of our output possibilities are listed right here. We have 4 possibilities. This is a very, very nice idea that we will right now will extend to operators that take in now 2 propositions. So let's go ahead and do that right now. We have unary operators. The next step up is what's called a binary operator. And a binary operator is exactly what you would think. If a unary operator takes in 1 proposition, remember this right here, I'll put a double line here. This star right here is not a special proposition. This is just something that we're doing to help us count and get at least some sort of idea of how many possible operators that we have. So remember, let's list this out. Binary operator, we have an input statement P, and we have an output statement Q. Sorry, an input statement Q as well. It's not an output. Q is an input in the case of binary. And then we have that we must list out if we're going to make a truth table, just like we did before. We need to make a truth table, but now it becomes a little bit more large because we have that P could be true and Q could be true. We have that P could be true and Q could be false. We have that P could be false and Q could be true, and P could be false and Q could also be false. So for binary operators, or in some sense it's a little bit of a larger problem because we now have a total of 4 possible inputs for each possible output that we might have for our operator. And let's, just like before, do this again. I want to emphasize that it doesn't matter here what we use. This is just like up here I use a star of P just to count the total number of possible outcomes for any given operator. You could, if you want to call it star, you could call it heart. Let's do heart. And now this is a heart of P and Q. So let's assume that this heart operator is a binary operator. It depends on P and Q. Well, just like before, we have a number of different situations. We have that heart of, if P is true and Q is true, heart of this true statement and this true statement, we have it could be a total of 2 possibilities. It could either be true or false for this input. For this input right here, so if P is true and Q is false, again, heart is just a proposition. So heart of, if P is true and Q is false, again we have just 2 possibilities. And same thing for the next 2 columns as well. We just have, for each one of these inputs, false true, true false, false false, or true true, heart of PQ, we have 2 possible outcomes, or 2 possible truth values that this can take on. And what that means, just like before, is that for binary operators now, remember before we were talking about unary operators, so function of 1 proposition, now we're talking a little bit more, we have binary operators. So, but again, we have, if this could be a total of 2 values, and this could be a total of 2 values, this could be a total of 2 values, and this could be a total of 2 values, then we have that the number of binary operators is 2 times 2 times 2 times 2, or 2 to the 4th, or 16. Right, so this is important. It's kind of jumping up to a much larger number of binary operators, even going from a unary operator to a binary operator. And likewise, we'll have a suitable, a large extension if we go up to ternary operators and so on and so forth. So the idea is we don't want to get ourselves lost in the notation here, so we want to be very, very careful. It turns out that we can prove that we only need to go to binary operators, that any statement that's that's very complicated and might involve a ternary operator or a larger number of operators can be rewritten in terms of just binary operators. So this is kind of a really nice theorem and a really nice idea. And what it means is that we just need to be familiar with not even all 16. We're going to see that we won't even need all 16 operations for binary operators. There's going to be a subset of these 16 that are very, very, very important to us. Okay, so let's try to wrap our heads around what type of binary operators we can have, or what the most important binary operators are to have. So I'll start off with the first 2, and I guess I'd say probably the most, not the most important. You can't really say that they're the most important, but they're very, very, very important. The first one that we'll start with is what's called the AND operator. It's the AND operator. And what this does is it takes a true value if and only if. So this if and only if statement also has meaning, but basically we're going to have that the AND, we'll define that later, and the AND operator though takes true value only only when both P and Q are true. So if P is true and Q is true, then P and Q is true. But if P is false, or if P is true and Q is false, then this AND operation or operator takes a false value. If P is false and Q is true, then this takes a false value. And if P is false and Q is false, then the AND operator also takes a false value because they're both false. This is the AND operator. And it's our first binary operator. The next is the OR operator. We have P or Q. Remember, this double line here means that these are our inputs in some sense, and everything to the right of the double line is our possible operators. But P or Q is what's called the OR statement. It takes a value of true for all possible scenarios unless P is false and Q is false. So for instance, if P is true and Q is true, then the OR operator takes a true value. If P is true and Q is false, then the OR operator takes a true value. If P is false and Q is true, then the OR operator takes a true value. And if P is false and Q is false, so if they're both false, that's the only time that this OR operation takes a false value. You might be a little bit confused by this because sometimes OR is confused with what's called the exclusive OR, which I will define right now. The OR operator has this truth table. This is mathematically what we define as the OR operator, and the AND operator, or the next operator that we'll talk about, is what the OR operator is sometimes confused for. It's what's called the exclusive OR operator. So this is written typically in one of two ways. You could put a circle with a plus sign in it. So this means P exclusive OR Q. And you also might be able to write it as, and this is how I do it in some of my notes, P, the OR symbol, but with a line under it, Q. These are two possible notations to denote what's called the exclusive OR operation. So exclusive OR is what I'm writing here in parentheses, but the main idea here is that this is very, very similar to the OR operation introduced before, but it takes a true value only if one of the statements is true and the other statement is false, and vice versa. So if they're both true, the exclusive OR statement is false, and if they're both false, then the exclusive OR statement is false. So exclusive OR really is just kind of, it's very, very similar to OR, and it's easy to confuse with OR, but it excludes the case where P and Q are both true. So this is a very, very important distinction to make and to understand the distinction. Now, if you want to, you can go ahead and fill out combinations using these and using the one, so using the unary operator. So these binary operators can be combined with unary operators to do all sorts of crazy things and come up with all sorts of crazy relationships. For instance, if I wanted to write out the statement not P and Q using the truth table here, well, not P and Q is the negation of this column of the truth table, so it evaluates to false, and then false for this statement. If P is true and Q is true, it evaluates to true because the negation of this is true, negation of this is true, negation of this is true. So this itself, negation of P and Q, is itself a new binary operator that we've constructed using one of our unary operators and one of our formal binary operators that we've constructed here. And we'll see that any sufficiently complicated logical statement can be written using just unary operators and binary operators. This is a very cool idea. But I guess the idea is that these three columns right here, these three statements are really, and the unary operators are going to be the basic building blocks for us as we move forward. The next step up is going to be what's called the implication operator combined with the equivalence operator as well. The next and arguably the most important of the operators, the logical operators, binary operators, is the following. It's called the implication operator. It is the one arrow right here between P and Q. This is called the implication operator, or the if P then Q operator, because mathematically what this is supposed to say, logically what it's supposed to say is if statement P, then statement Q. That's what this means. And what this takes on is the following truth values. Remember, we're defining all these logical operators in a very specific way so that they behave very, very nicely with regards to traditional logical ideas. And this is why the implication operator is defined as such. We say that if P is true and Q is true, then the implication P implies Q is true. If P, then Q is true. It is going to be false if P is true and Q is false, and this evaluates to false. And this is the somewhat surprising statement to a lot of people, and specifically to beginning math students. We say that if we start with a false, a false input P, then the implication will be true regardless. So this will be true. This will be true whenever you start with a false starting value or starting statement. And this may seem somewhat confusing to beginning mathematicians or beginning computer scientists. But there is a very, very nice logical basis to this. And specifically, it's in the following statement. It relates to the Latin principle ex falso quod libe. So let me write this down, it's important. Ex falso quod libe. And the idea is that all of our principles of logic and all of these logical operations that we're defining have to be based off of nice, good principles of Latin logic, of solid logical principles. And really, this last statement right here, that if you start with a false assumption, you can prove anything, is the statement ex falso quod libe. Roughly translated, it means from false assumption, or from a false assumption, anything follows. Right, and this is why the implication operation right here in this column takes on a value of true, even if you have that P is false and Q is true. It's sometimes a hard thing to understand, but we have to have this in some sense. And specifically, we can see this even stronger when we think about what's called the by implication operator. So you always want to kind of think of these two things together. And we really see an example of this when we consider the connection between implication and by implication. So by implication, just like or similar to implication, is we say that it's two arrows this time. So the by implication operator is a P, a Q, and then a double arrow in both directions. I guess now it's important to say too that in some of the notes, as well as in certain notations, for implication you'll see a double arrow. This means the same thing up here as this does right here. It just depends on the author. Similarly, for by implication, you might see the double arrow. where P implies Q and Q implies P. The by implication really stands for an implication in both ways. And we'll really see that clearly when we investigate the connection between these two things in terms of what's called logical equivalences. But the by implication is defined to be true when both P is true and Q is true, or when both P is false and Q is false. So it's the operator that's defined as true if both P and Q are true, but it's false when either one of them is false and the other one is true. So when they have opposite truth values. And if both are false, then the by implication ends up being true. This is what's called the by implication operator. And what's nice about this operator is that this has a very, very close relationship to the implication operator. I said before that you can really think of the by implication operator as being an and statement between the P implies Q and Q implies P. And we can really make this exactly, very, very, this nice connection in terms of the following. If we I'll draw a copy of this truth table just so that we can kind of put a little bit more into it. But let's say we have two statements, P and Q, where P it can be true, true, false, false. Q could be true, false, true, false. This gives us all of our possible inputs to our operators, for binary operators, I should say. And now what we're going to look at is we're going to look at P implies Q, which is our implication statement. So we know this is true. If it's true and then false, this evaluates to false. And then for everything else, it's true. And we can consider what's called the converse. Q implies P. So this is what's called mathematically the converse of this implication. And you can see a fundamental difference between the converse and the implication right away, that the converse is going to evaluate to true, and then, this is Q is false implies a true. This is going to evaluate to true because we're starting with a false statement. And then we have true to false gives us a false implication, Q implies P, because we're going from true to false, where we're going in the direction Q to P here. And then lastly, false, false, because we start with Q false, this evaluates to true. And we see something very interesting happen here when we write down the and statement between these two statements. So the and statement between the implication and the converse implication. This and statement, P implies Q and Q implies P, ends up being, well, this is true and this is true, so the and statement between these two is true. This is false and this is true, so the and statement is false. This is true and this is false, so the and statement between these two statements is false. And then lastly, this is true and this is true, so the and statement between them is true. And what we see very, very nicely illustrates the following concept. So if we rewrite our truth table for how we define the by implication as true, false, false, true, we see very, very clearly that these two columns are equal to one another. And because of that, this equality here, we can say that these two statements right here are logically equivalent to one another. This is in some sense the definition of logical equivalence. So I'll write this down right here just to be exact. We say that if S and T are propositions, are two propositions, we say that S is logically equivalent to T if the by implication, so that this statement S by implication T, so this statement right here, is a tautology. And another way of writing tautology or contradiction, you can write like something like this. This means that the by implication S implies T and T implies S is a tautology. So I guess for this example right here, then, I guess what I'm trying to show here is that this is how we define logically equivalent, two logically equivalent statements. And what we've just shown over here is the following. We've shown that if S, we'll just assume up here, if S is this statement right here, the statement P implies Q and Q implies P, and we'll also define, so this is what we're going to call S, this statement right here, this entire statement, and T is this statement right here. Well, T, the by implication that we defined before. Then S by implication T is a tautology because these two have the same value, these two have the same value, these two have the same value, and these two have the same value. So this is a nice picture kind of showing what it means to have the by implication be a tautology. It's the main idea is that because in this column is a tautology, we have all true values. That means that S is logically equivalent to T. So this statement right here is logically equivalent to this statement right here. Now, we can make more complicated statements, and the general idea here is that by implication and logical equivalence is used very heavily when, say, taking a truth table or taking two statements. If I can show that one statement S is logically equivalent to T, and then I can prove that T is true, or I can prove statement T, then statement S is also proven. So this is kind of a very neat idea that ends up being applied very, very, very often in mathematics. But what I've just done is I've shown you the fundamental reason why the implication operator has to be defined the way it is. It's essential that it's defined this way so that the by implication operator is logically equivalent to P implies Q and Q implies P. So it's a very, very nice kind of picture. This propositional logic that we have so far is an extremely nice picture that's essentially allowing us to do a whole number of different very, very interesting things. And the tools that we have so far is basically kind of starting with what we've done so far. So all of these operations that we've done so far, the implication, the by implication, and or these in negation, these are really our basic building blocks now, because one of the big theorems that we have is that, and this is the theorem that I talked about at the very beginning. Let's say we have some higher order operator that may depend on n statements. So just like, for example, suppose, and we'll just use heart again, heart of P1, P2, Pn is an nth order logical operator. The result that we have, and I'm not going to prove this, but it's possible to do it it's relatively straightforward to do. We have the following theorem. Any higher order operator that looks like heart, some general nth order operator can be constructed from the binary and unary operators. So this just gives us kind of it's a nice result that we have, and we can be safe to have faith that any logical operation or relationship between propositions you can construct can be constructed and I guess decomposed into just these binary and unary operators. So the negation, the and, the or, and the implication operators. And this is a big idea, because it means that we don't have to go through the process of defining logical operators for ternary operators and so on and so forth. That this is really kind of a universal language that we can write mathematics in. That's the kind of the power here. So I'm going to finish up this lecture by basically writing down a couple more useful logical equivalences that are going to be very useful in the coming lectures. So the first one is what's called, I talked briefly before about the converse. We can form a number of new statements as well that are similar to the converse but all have different meanings. So for example, we're just arguing based solely on truth tables for the moment. So if you remember, we have P implies Q, or if P then Q. This is going to be true only when, or it's going to be true everywhere except for when P is true and Q is false. That's true here, true here. So if this is our implication, we defined before the converse. Of an implication is just the reverse implication, and it's important that you realize that the converse, when you go through and do this, well, if Q is true, P is true, then this becomes true. If Q is false and P is true, then this is evaluated to true. If Q is true and P is false, this evaluates to false, because Q, the preceding statement, is true, but the then statement is false. And then this becomes true as well. So it's really important that you see that this is the reason that the implication is in general different than a converse. And mathematically, if you prove an implication, you do not have that converse. You have to, in general in mathematics, we try to show what by implications, which means that we try to show the implication both ways. This is in some sense a stronger result mathematically than just proving one way implication, a one directional implication. But we do have a nice logical equivalence with what's called the contrapositive in the implication. And you can think of the contrapositive as the following. The contrapositive is not Q implies not P. And this might require a little bit of additional kind of work to see a little bit. So I'll move this back a little bit. So you're going to want to remember that the negation operator of each one of these, if this is not P and this is not Q, not P is going to be false, false, true, true. Not Q is going to be false, true, false, false, true. And what we end up getting when we do not Q implies not P is we're moving in this direction from not Q here to not P. So here it evaluates to true. We're going true to false. This if this is true and this is false, then in this direction, not Q implies not P is going to evaluate to false. Again, we're going from not Q to not P. So if we go false to true, this evaluates to true. The implication evaluates to true. That's our principal ex falso quad lib. And lastly, if we go true to true, this implication evaluates to true. So what you should see immediately is very, very nice, is that the implication, P implies Q, is logically equivalent to the contrapositive. These two statements have the exact same truth tables. So just to clarify, remember that means that the by implication, so P implies Q, by implication with the statement not Q implies not P, what logically equivalence means is that this by implication is a tautology. So we have the same truth value here, the same truth value here, the same truth value here, and the same truth value here. It's important to point out that logical equivalence is in the book, and I will sometimes also write it in a certain notation. Instead of writing this by implication between the two statements, it's sometimes just easier to write 3 lines, so like equals, but it's not equals. These 3 lines means that the statement on the left is logically equivalent to the statement on the right. And this logical equivalence specifically right here that we've just shown, this is just one example of one. It's a very, very important one, and it's actually what proof by contradiction is based on in mathematics. So, proof by contrapositive is based on, not proof by contradiction. That's a different thing that we'll talk about later on. But proof by contrapositive is the act of proving the contrapositive of some statement you're trying to show. It's very, very useful in mathematics. So we'll get into that a little bit more when we talk about proof methods in mathematics. Proof by contradiction is another way of proving something in mathematics as well, which we'll get into as we go over various proof methods. But this is a very, very big, the contrapositive, this is a very, very big, good example of a logical equivalence. You have another example of important logical equivalence that we'll show in just a second. But the last, I guess, implication function that we can have is what's called the inverse. And I'll just continue this column right here by shifting this table over a little bit so we can write down the inverse, because this is the last thing that you might see in terms of this idea of the implication operator. So move that over here, and just kind of continue this down the line. So we have that we have the implication, converse of the implication, contrapositive of the implication. The inverse is just like it sounds. It's just this is called the inverse implication. It's just the statement not P implies not Q. Which again, just like before, is if we consider our column or our row of nots, the not operator applied to these statements, not P implies not Q is going to be true for this first row. It's going to be true for the second row because we're starting with a false implication, or starting with a false precedent, which will automatically give us, sorry, not a false, but a true implication. Here we go from true, not P is true, to not Q is false. So the if-then will evaluate to false. So we're going from a true to a false. And then because we're going from a true to a true, this evaluates as true. And you see exactly, in some sense, the reverse of this logical equivalence, which is that the converse statement is actually logically equivalent to the inverse statement right here. So I'll circle the logical equivalences in the corresponding colors. Probably erase these circles right here and put in circles or put in circling corresponding to blue. So here you're seeing that I just showed you that the statement P implies Q is the same as the contrapositive. It's two logically equivalent because these two columns are equal to one another, and likewise the converse and the inverse are logically equivalent to one another. So now we also have a useful logical equivalence is that not Q implies not P. Sorry, not P implies not Q, or the inverse is logically equivalent to Q implies P, which is almost like saying the contrapositive of the converse is equal to the inverse. Is the same statement. The next example, and I think I'll move on to this is probably the last example that I'll go over today, or the last two examples we'll go over today, is the following. We'll start with what's called De Morgan's law. And a lot of people think that De Morgan's law is an idea in set theory, and it is, but really it gets its roots from propositional logic. So and this is very, very, very important. De Morgan's law is something we'll be using time and time and time again to simplify logical statements and to derive new logical equivalences. The main idea here is that we don't always want to be drawing these truth tables. So gradually we're going to become less and less reliant on the truth tables and more reliant on using logical equivalences to make simplifications. And on certain assignments, I'll ask you to check with the truth tables, but I'll ask you to do the main portion of the assignment using just logical equivalences. So you're going to want to know both methods. You should know how to use a truth table, and you should also know how to use logical equivalences to simplify certain logical statements. So De Morgan's law is the following statement. We consider the negation of P and Q. So remember, we'll take P and Q. Well, first we're going to be doing a lot with negation. So I'll first make a column for not P. Or not column, but row. And I'll make a row for not Q. So it becomes false, true, false, true. We're really just doing the opposite of each of these statements for the negation statements. And then remember, we'll do P and Q. So P and Q is going to be true, false, false, false. And if we just consider, let's just for instance consider the negation of P and Q, so not P and Q, not P and Q, and this is P and Q, so this is going to be false, true, true, true. And this might seem like I'm just kind of pulling stuff out of thin air, but I swear to you that I'm not. Let's also now consider the statement not P or not Q. So this is not P or not Q, so we end up getting false, because not P or not Q this ends up being false. This ends up being true, because not P is false, but not Q is true here, so the or statement between these two is true. And then likewise it becomes true and true. And what you should notice almost immediately is what's called De Morgan's first law. That this statement right here, not P and Q, is logically equivalent to this statement right here, not P or not Q. So this is a huge, huge result. I can't really emphasize how strong of a result this is. I really don't want to de-emphasize at all how strong this result is. That this statement right here is logically equivalent to the statement not P or not Q. And this is De Morgan's first logical equivalence, or De Morgan's first law. And it's funny because the De Morgan's law in set theory that we will see eventually is really just based on this this logical law. So there's no set theory at all. De Morgan's law is not a set theory thing. It's in some sense a deeper mathematical relationship that is something that's dependent on the logical system that we formed for writing down our mathematics. We have a similar De Morgan. So this is sometimes known as like the first De Morgan's law. We have a similar De Morgan's law, and I'm not going to do it out right now, but I recommend doing the truth table out. It's the statement that the statement not P or Q is logically equivalent to the statement not P and not Q. So this is sometimes said the negation of an and is the or of the negations, and the negation of an or is the and between the negations. These are going to be really, really, really important for us going forward in terms of simplifying possibly very complex logical statements. So we're really going to want to be familiar with De Morgan's law, specifically because of this reason. We're going to end up using it to simplify very long and complicated statements. This is very, very, very important. A very, very, very important example. So please remember this, not just this logical equivalence, but how to show it as well. Because a lot of these logical equivalences, if you forget them, you can always go through and rederive them using the truth table. So there are going to be certain problems that I give you where you have to use the logical equivalences. But if you forget a logical equivalence, you can always rederive it using the truth table, which is a very, very nice way of thinking about things. So I'll go over the last logical equivalence. We have one last and final example. Now, I'm writing down examples here, but the point is that these are really, really big things that you should commit to memory, because all of these examples that I've shown right here, especially all of the notes that I've gone over today, are going to be like fundamental in terms of solving problems in the future and solving possibly more complex logical problems. So the last example that I have for you today is the logical equivalence that P implies Q is logically equivalent to the statement not P or Q. And we'll see this very clearly if we just kind of do out the truth table, just like all these other expressions. So we do row for P, row for Q, true, true, false, false, true, false, true, false. And we know we want to do, we know that P implies Q is true. This is going to evaluate to false, true, true. And then we know that not P is false, false. It's negation of P, true, true. So that not P or Q is going to be, well, this is false and this is false, which means not P or Q evaluates to true. This is false and Q is false, which means that not P or Q evaluates to false. Not P or Q, if this is true and this is true, evaluates to true. And lastly, not P or Q, if P is true and Q is false, evaluates to true. So what I've shown here is that this statement, the statement P implies Q, is logically equivalent to this statement right here, the statement not P or Q. Or if you will, in terms of our larger definition, we have that the statement not P or Q is a by implication, or the by implication not P or Q with the statement P implies Q is a tautology, because these two have the same truth value, these two have the same truth value, these two have the same truth value, and these two have the same truth value. So this statement is a tautology for any propositions P or Q, which means that this logical equivalence has been shown. I've shown it. This is really, really important. It turns out that this logical equivalence is extremely important in proving things, because very often what we can do is use this to, along with De Morgan's laws, to come up with like nice what it means if I have an implication, what it means to have the negation of an implication. So this is just another example. If I want to use logical equivalences and stay away from truth tables, I can say that the negation of P implies Q is logically equivalent to the negation of not P or Q. This is from De Morgan's law. Sorry, not De Morgan's law. This is just from the what we just showed. I'll call it call this example example star. So from star, we have that P implies Q is the same thing as not P or Q. Now it's De Morgan's law. So from De Morgan's law, we can say that not P or Q is the same thing as not P and not Q, because this is De Morgan's law. We're saying that the negation of an or statement is the same as the negation of the first statement and the negation of the second statement. And then we have another logical implication that I'm not going to prove right now, but I recommend you do it when you get home. We have that not P is logically equivalent to the original statement, or the double negation of P is logically equivalent to P. You can prove this relatively straightforward just making a truth table by yourself, so I recommend you do that just for practice. But what we have is then that this is the logically equivalent then to P and not Q. So what we've shown is that the negation of an implication is the same thing as, so then the negation of if P then Q is the same thing as P and not Q being true or false. So this is a nice stopping point, because at this point now you have enough machinery to start working on basic logic problems, so basic propositional logic problems, and you can kind of go through and work through some of the examples that I've posted. But thanks for tuning in, and have a great day.